Alright, so we're going to go ahead and discuss how the nerve signal actually travels down the axon. So remember that the signal would be received by the dendrites up here, moves through the cell body, and then we're going to get to the axon. The myelin sheath is going to control the speed of the impulse, and here at the nodes of Ranvier, that is where we are going to see action potential, which is what we're discussing today. So I have a very simple diagram. We're going to keep everything super simple. It doesn't tell the whole story. In reality, between the myelin sheath, we would have lots and lots and lots and lots of these channels. But we're just going to keep it super simple here. So this is meant to represent resting potential. At resting potential, we have sodium outside of the cell and potassium inside of the cell. Along with the potassium, we have all these different negative ions. All these little green marks represent negative charges. So this is RNA, phosphates, sulfates, ATP, all kinds of molecules. But we'll just keep it simple and put those negative signs. Now, in reality, even though we're going to represent resting potential where all the sodium is outside and all the potassium is inside, that is not completely true. We do have a tendency for the things to want to equal out within the cell. So some sodium would want to move over here so that there's equal sodium on both sides, and some potassium would want to move over here so that there's equal potassium on both sides. The potassium tends to move easier through the membrane, so that is how we actually really keep the inside of this cell negative and the outside more positive. But for simplicity purposes, we're just going to keep potassium inside of the cell, and the inside of the cell, again, is negative because we have all these negative ions. And in addition, we have more positive ions outside of the cell than inside. Redraw these so you can see them. Okay, a bunch of negative signs. Okay, so the inside of our cell is negative. So let's go over to the notes part and see what we would be drawing here for resting potential. All right. So I'm going to do red sodium to go with my red channel. So to represent resting potential, have that. And what's important is, so because we do technically have some of these leaking this way and some of these leaking this way, we have to have this sodium-potassium pump active to keep this balance where most of the sodium are here and most of the potassium are here. So the sodium-potassium pump is going to be pumping 3 sodium out of the cell and 2 potassium into the cell, and that's going to require energy because it's working against the electrical gradient. It requires ATP. Okay, and then you should go ahead and fill in some negative signs here for those other negative ions. So at this point, if you look overall, the inside of the cell is negative. Okay. And you can also see that there's more positive charges outside of the cell than there are inside of the cell. Okay, and that's why we keep this ratio of 3 to 2, so that we have more positive charges outside of the cell than inside of the cell, because each one of these ions has a positive 1 charge. Okay. So if you're removing positive charges, then it gets more negative. If you're adding more positive charges, it will get more positive. Okay. And then we'll put positive up here. So what's happening here? Most sodium, and I put most, not all, is outside the cell. Most potassium is inside the cell. And the cell is negative. Okay, negative 70 millivolts to be exact. So let's say that we get a nerve impulse. So our dendrites receive a signal. Once we reach the threshold of a certain charge of about negative 55 millivolts, this channel is going to open up. Okay, and these channels work in one way. Sodium can only move through this way, and for potassium, potassium can only move out that way. So what's going to happen is once we receive that nerve impulse, if it's strong enough, we're going to this gate is going to open up, and sodium is going to start rushing into the cell. Okay, and just to make things go a little faster, let's pretend this is going through the channel. Okay, now we've got a whole bunch of sodium inside of the cell. So we brought a whole bunch more positive charges in. Okay, so what's happened is our cell has become more positive. So let's go back over to our notes. And what we're going to demonstrate is we're going to make this look real simple. We're going to show sodium going in to our sodium channel and ending up over here. Okay, we still have all those negative ions. They're not able to leave the cell. I'll draw those in. And potassium is still inside of our cell. Okay, so since we're adding more positive charges, the inside of the cell becomes positive. We'll make a little note of that. Adding more positive charges makes the cell positive. Okay. So what happens during depolarization? So polarization, by the way, is that idea that we have a negative interior of the cell. We have a difference of charge on either side. So during depolarization, sodium channels open, sodium rushes in, and the cell becomes positive, okay, because we're adding positive charges. Okay, so that was depolarization. Okay, so we're reversing that negative charge, right? We went from a more negative interior of the cell to now a more positive interior of the cell. Okay, back here. So now what's going to happen is the sodium can't go back through this way. Okay, this gate is now going to close, and my potassium channel is going to open. And potassium is going to leave, so it's going to go through there, and I'm just going to stick them on the other side for the sake of time here, but they can go through that channel. Okay, now we have positive charges leaving. So the interior of the cell is becoming less positive. In other words, we're bringing our cell back to negative. Now, I didn't include this in your notes, but this is actually going to go too far, and it's called hyperpolarization. But we're able to fix that in the next step. Okay, so this gate had closed, so no more sodium is coming into the cell. And now this gate opens and potassium is going out of the cell. So let's go ahead and draw that on our notes. I'll write it in first. So sodium channel closes, so no more sodium can go into the cell. the potassium channel opens, potassium rushes out of the cell, and as a result, because we're losing those positive charges, the positive charges were leaving. So it's like money exiting your bank account, right? It's going to get closer and closer to a negative balance if you keep losing dollars. Same thing with these ions. So what's going to happen is the cell becomes negative. Okay, and again, I left out the part about hyperpolarization for simplicity purposes for these notes. So we had all these sodium, and I'm going to exaggerate here. Not all of the sodium will be inside of the cell and all the potassium outside of the cell, but just so that it makes it easier for you to understand when you look back at your notes, I'm going to exaggerate it here. So we're going to show potassium is going into that channel. Okay, all the potassium is rushing through to the outside of the cell. That's what's happening in that picture. Okay. So now the cell is negative. We lost positive charges. So the cell becomes negative. All right. So how are we going to get back to normal? Well, remember we have this sodium-potassium pump that is going to work against the concentration gradient. So what's going to happen is this sodium-potassium pump is going to be working to get everything back to normal. We want sodium to be, for the most part, outside of the cell and potassium to be inside of the cell. So what we're going to do is the pump is going to take 3 sodium from the inside and 2 potassium from the outside and put them back where they belong. And again, this ratio is so that we have more positive charges outside of the cell than inside of the cell. Okay, so again, I'll do another example. I'm going to take 3 sodium from the inside, and I'm going to take 2 potassium back inside. Okay, and it will do that until we get our cell back to resting potential. So I'm going to show here that we are doing 3 sodium back out, 2 potassium back in, until we go back to resting potential. And I apologize, I forgot to draw in the negative signs for those other examples, so let's go ahead and do that right now. And I'm going to highlight this. So what's happening here is that we're trying to get it back to this normal, and the way it does that is through this sodium-potassium pump. So the cell will become negative again. So I'm going to draw my negative signs here. Okay, the cell is negative because we go back to resting potential. So the sodium-potassium pump sends 3 sodium back out, 2 potassium back in, until back to negative 70 millivolts. Okay, and then again, this requires energy. You actually use more energy, or a significant amount of energy, just trying to keep your cells at rest versus actually doing it, than actually sending the signal. Okay. I'm going to run through that over here again. Okay, so here's my resting potential where most sodium is outside the cell, potassium's inside the cell, along with all those negative charges. So this is resting, cell is negative. We're going to receive a nerve signal. It goes through the dendrites, makes its way to the axon. Once we reach the threshold for the charge, these gates are going to open. Sodium is going to rush through into the side of the cell. Once we get to a positive 40 millivolts, this gate is going to close. Okay, so that was depolarization, right? We reversed the charge, so the cell is very positive because of all the positive charges. Now we're going to reverse. We need to repolarize, get back to negative, and we're going to do that through the potassium channel. So it's going to open up, and all this potassium is going to rush out of the cell, okay, through that channel. Okay, and then we need to get back to resting potential, where we are going to use the sodium-potassium pump to take 3 sodium, move them back to where they belong, along with 2 potassium back to where they belong. And then it'll keep doing that until we get back to normal.